Hello, and welcome to Cruising Through Calculus. My name is Alex, and today we're going to be talking about polynomial end behavior. Before we jump straight into the end behavior, I wanted to give you a quick rundown of what polynomials look like versus what they do not look like. So, let's take a look at that right now. Over here on this side are all examples of things that are polynomials, and over here are all examples of things that are not polynomials. All I've done is taken one thing from here and changed it, and that change turned it into something that's not a polynomial. So let's go through it line by line. For the first one, we have y equals x squared minus x minus 20. That is a polynomial. Over here, we have y equals x squared minus the square root of x minus 20. That is not a polynomial, and the reason why is because we're taking the square root of a variable. If you ever see the square root or the cubed root or the fourth root of a variable, that automatically is not a polynomial. Now that doesn't mean that square roots are not allowed. In this next example, I have the square root of 17 right here, times x to the 1,000th minus pi x to the 17th plus e. You can actually have any number you want in front of your variable. It doesn't matter if it's the square root of 17 or an irrational number like pi, or even e can show up. All of those are fine. Let's compare this to this and see what the difference is. I think you'll see it right away. It's the square root of x, or square root of 17x to the negative 1,000. If you ever see negative powers, that automatically is not a polynomial. Here we have negative 16t squared plus 100t plus 20. This is fine as a polynomial. I may have changed the letter from x to t, but that's perfectly fine to do. You can actually use whatever letter you want, although x is definitely the most common. Over here, I've made one change. Instead of t squared, I made it t to the power of 1/2. If you ever see fractions in your powers, then that automatically means it is not a polynomial here. I do want to be clear, the fractions can have powers of the numbers, like we could have 100 to the 1/2. That's fine. But if the variable is raised to that fractional exponent, that means it's not a polynomial anymore. Lastly, we have y equals 3/2 t plus 1. That is a polynomial. And over here we have 3 over 2t plus 1. The difference is that this t is now in the denominator here. If you ever see the variable in the denominator, that means it is not a polynomial anymore. In fact, what's kind of interesting is that if you take a variable and raise it to a fractional power, that's the same thing as, say, taking the square root of t. So my first example and my third example here are actually the same idea. Both of them have variable to a fractional exponent, or just a radical, if you will. Similarly, my second and fourth examples are actually the same thing, because if you ever have something raised to a negative power, you can take that and move it to the denominator here. So, for example, down here, 3 over 2t could be written as 3 over 2t to the negative 1, like this. And so in that sense, these are both examples of the same thing. Why don't we jump into the end behavior, though, because that is really what we're here to discuss. All polynomials have a leading coefficient and a degree, and you need to know what those are if you're going to find the end behavior. I'm going to be abbreviating leading coefficient as LC and degree as DEG. When you're looking at a polynomial, what you need to do is find the power that is the largest. Most of the time, that's going to be written in the very first term here, but that's not always going to be the case. In this example, the largest power is right here, 4. And in fact, when you find the largest power, that is your degree of the polynomial. This is a degree 4 polynomial. The leading coefficient is the number that is attached to that piece. So in this example, negative 16 is the leading coefficient. Once you know this and can recognize it, you can find the end behavior of polynomials. There are 4 possible outcomes for the end behavior of polynomials. And here's what kind of information you need to extract from the polynomial to know which end behavior is which. If you find that the degree is an even degree, and if you find that the leading coefficient is positive, What that tells you is that the end behavior of the graph will have both sides pointing up like this. Remember, we're talking about the end behavior here. I don't really care what happens in the middle at the moment. I care what happens as you let x get really big, or as you let x get really big in the negative direction. The next possible outcome is that the degree is still even, but this time your leading coefficient is negative. What that tells you is that the end behavior will look like this, meaning that as you move to the right, the graph will go further down, and as you move to the left, the graph will also be moving further down. The third outcome is if your degree is an odd degree, and your leading coefficient is, say, positive. That means that the ends of your graph will be pointing in opposite directions, like this, one up and one down. The last outcome is if your degree is odd, but your leading coefficient is negative. The arrows are still going to be pointing up and down, but this time they're going to be doing the opposite, like this. I highly recommend taking the time to memorize these. It actually isn't too bad when you take a look at it. For example, notice an even degree has the arrows pointing in the same direction, whether the leading coefficient is positive or negative. The only difference is where they point. And an even degree in positive points up, well, that kind of makes sense because positive and up go together. And over here, even and negative means they both go down. Where things get a little strange, maybe, is remembering the odd and positive and the odd and negative one. You can remember that the arrows point in opposite directions if the degree is odd, but remembering exactly which one is which is the tough part. But it isn't that bad, actually, if you think about it this way. As you move further right in the positive direction and the arrow points up, that's also positive. So the leading coefficient being positive matches with that. Go to the right, go up, positive. Over here, as we go right, we're going down, which is negative. So try to think of it that way. As you move to the right, what does your graph do? Well, if you have odd and positive, that means moving to the right goes up because it's positive. Over here, if it's negative, that means you're moving right and you go down. Since you can remember that odd means they're pointing in opposite directions, you can figure out the other one pretty easily. The reason why knowing end behaviors of polynomials is so helpful in calculus is because you're going to be running into limits as x approaches either positive or negative infinity. This is actually just a very fancy way of them asking you, what is the end behavior of the function you're looking at? Well, if you know the end behavior of polynomials, that can help you in certain cases. In this example here, I immediately notice that the leading coefficient is negative and the degree is odd. The degree is odd means the arrows will be pointing in opposite directions, and negative means that as we move further to the right, the graph will go down. So I know my end behavior will look like this. Now that I know that, as x approaches infinity of this function here, well, as I move further to the right, my graph goes down, so my answer here is negative infinity. This is great for polynomials. It can even work for things that are not polynomials, like this. This is a rational function here. Now you can't just immediately use the end behavior here because you have one polynomial divided by another polynomial. But what you do instead is you recognize the largest piece in the numerator and compare that to the largest piece in the denominator. Like this. Then we simplify. After you simplify, you can use your knowledge of end behavior. Positive leading coefficient, even degree. That means both arrows pointing in the same direction. Positive means both arrows pointing up, like this. So, back to our limit, as x approaches infinity, so as we move further to the right, our graph is going straight up. Feel free to use this when you're using limits at infinity of polynomials or rational functions. If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.